Now that we have seen how to compute Taylor polynomials and use them to estimate, let's talk about how accurate these estimations actually are. First, recall that if f of x equals the sum of its Taylor series near a, then f of x is equal to the limit as n goes to infinity of t sub n of x. All we're saying here is that the Taylor series is, by definition, equal to the limit of its partial sums, which are exactly the Taylor polynomials. But this implies that as n gets larger, t sub n of x becomes a better approximation for f of x near a. And now the problem is, the further that x gets from a, the weaker this approximation t sub n of x becomes when we fix n. To compensate for this, we must take large enough values of n to get an approximation that is close enough for the values of x that we care about. But how large is large enough? The process that we will use to bound the error will be similar to the one we used for alternating series. First, let r sub n of x be the error in approximating f of x by t sub n of x. Then there are two ways that we could estimate this error. First, if the Taylor series happens to be alternating, we can go ahead and use the alternating series estimation theorem from the previous lecture. If it's not alternating, however, then we can use something called Taylor's inequality, which says that if the absolute value of the n plus first derivative of f is bounded by some number m for an interval of radius d about the point a, then the error r sub n of x satisfies the equation absolute value of r sub n of x is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1 for all a in this interval. So that was a lot to process. Let's see how to actually apply Taylor's theorem by looking at some examples. All of these examples will involve the function e to the x. So first, let's recall that the fourth degree Taylor polynomial of e to the x centered at 0 is given by 1 plus x plus a half x squared plus 1/6 x cubed plus 1/24 x to the fourth. And now let's figure out how to apply Taylor's inequality to this function. The first part of Taylor's theorem involves finding a bound for the n plus first derivative of f. In our example, we're approximating with the fourth degree Taylor polynomial, so we want to find an upper bound for the fifth derivative of f. So our first problem will be, what is the fifth derivative of f? Is this derivative increasing or decreasing on the interval -4 to 4? And then find an upper bound for the fifth derivative of f on this interval. The first question is pretty straightforward. Since our function is e to the x, any derivative of that function is e to the x. Moreover, we know from the graph of this function that e to the x is always increasing. And so where does an increasing continuous function attain its maximum? It'll have to be on the right endpoint of the interval. Therefore, the fifth derivative of e to the x, which is e to the x, is bounded above by e to the fourth on the interval -4 to 4. Now, the last part of Taylor's theorem involves finding an upper bound for the remainder r sub n of x. So let's try to apply this part to our example. That is, let's use Taylor's inequality and the upper bound from part A to find the accuracy in approximating f of x by t sub 4 of x on the interval -4 to 4. In order to use Taylor's inequality, we need a good value for m. However, we found in part A that the fifth derivative of f is bounded above by e to the fourth on the interval -4 to 4. So we can use Taylor's inequality with m equals e to the fourth to get that the error r sub 4 of x is bounded above by e to the fourth over 5 factorial times the absolute value of x to the fifth. But on the interval -4 to 4, the absolute value of x is bounded above by 4. Therefore, this quantity is less than or equal to e to the fourth over 5 factorial times 4 to the fifth. And if you plug this into a calculator, you'll find that this is about equal to 465.9. So that's pretty huge. So what if we wanted to do any better? Well, we'd either have to take a higher order Taylor polynomial or consider taking a shorter interval. Let's try shrinking the interval to improve the approximation error. In particular, let's find an interval around 0 for which this approximation has error less than 0.001. Let's rephrase this using r variables. We want an interval, absolute value of x less than or equal to r, on which the error r sub 4 of x is bounded by 0.001. Note that r has to be less than 4, since the error on the interval -4 to 4 was over 400. So, then what is our goal for finding this r? Well, since r is less than 4, we still have that the fifth derivative of f, which is e to the x, is bounded above by e to the fourth on the interval minus r to r. So we can still use that m is equal to e to the fourth. Then we want to find an interval minus r to r so that e to the fourth over 5 factorial times the absolute value of x to the fifth is less than or equal to 0.001 on this interval. Because then, by Taylor's inequality, we have that the error, which is bounded above by e to the fourth over 5 factorial times the absolute value of x to the fifth, is bounded above by 0.001, which is exactly what we wanted. So let's find this interval. We want e to the fourth over 5 factorial times absolute value of x to the fifth to be less than or equal to 0.001. And now we can solve this inequality for the absolute value of x to find that the absolute value of x must be less than or equal to 0.294. Therefore, the error r sub 4 of x is less than 0.001 on the interval absolute value of x is less than or equal to 0.294, which is the same as the interval negative 0.294 to positive 0.294. And so we're done.